All right, let's get rolling. Welcome everyone to our session. Firstly, a big thank you for coming to this evening session. It's day 3. It's late. For those of you who made it, we really appreciate it. So, a big thank you for coming this late in the day. reInvent is in person. It's been virtual over the last 2 years. It's definitely more fun doing this live versus doing it sitting in the corner of my room in front of a camera. So it's exciting to see some of you live, and I think hope to keep doing this in the next few years as well. This is session DAT327. We're going to talk about how Intuit migrated Apache Cassandra workload to Amazon Keyspaces. We're also going to give you a quick overview of what Keyspaces is, especially if you've never used it before. With that, my name is Meet Bhagdev. I am a principal product manager at AWS. I lead product for Amazon Keyspaces. I'm joined by some really talented folks from Intuit, Manoj Mohan, who is an engineering leader at Intuit, and Jason Lashmith, who is a principal software engineer and the pioneer of some of the migration things that you're going to learn about on the technical side. With that, let's get started. We have an action-packed agenda for you. We're going to talk about what Cassandra is, what Keyspaces is. We're going to talk about our architecture. It's a question that we hear a lot from a lot of our customers is, okay, how are you really built? So we're going to cover that just a little bit. We're also going to talk about how Intuit migrated to Keyspaces and some of the benefits that they have experienced from their migration to Keyspaces. Before we talk about Keyspaces, I want to talk a little bit about Cassandra. So Cassandra has been available, I want to say, for about 14 years. Some of you may be using it in production today. Some of you may have just heard about it. It's founded by the Apache Foundation. It's one of the original projects by Apache. It's used for a variety of workloads. Customers use it for any kind of applications that need massive scale with low latency performance. That's where Cassandra really comes in. It also integrates really well with other projects in the Apache community, such as Kafka and Spark. And last but not the least, it actually gives you a SQL-like query language called the Cassandra Query Language. It's a wordplay on SQL. They call it CQL, which a lot of customers like to use, especially given it's a NoSQL database. If you've done relational before, it gives you the best of both worlds with the scale from NoSQL and the query language from maybe a relational background. With that, we do hear from customers that managing Cassandra is still painful. It scales well, but comes with a cost, right? You need to deal with backups. You need to deal with dynamic scaling, which talk about adding nodes, removing nodes. This is painful. Patching could cost downtime sometimes. Version upgrades, again, you got to plan for that. Some of these database operations are really, really painful on Cassandra, and that's where Keyspaces comes in. Before I get into Keyspaces, of all the folks here, can I get a show of hands if you've used or heard of Keyspaces before? All right, it's a decent number, and by the end of it, for the folks who did not raise your hands, hopefully you could turn those to yeses as well. But Keyspaces is AWS's fully managed, Cassandra-compatible, highly available serverless database service. Now, I threw a lot of words at you. You're probably wondering, what is this salesy pitch that you're talking about? We're going to break it down into 4 kind of segments here. The first one is Cassandra compatibility. This is really important to us. So if you're already using Cassandra today, you can use Keyspaces with the same application tools and drivers that you're using today. So you don't have to learn a completely new set of tools, libraries, SDKs, command line tools, GUI tools. Pick your favorite tool that you use today. Our goal is to make those work with Keyspaces. Now, I have a full slide on how we define compatibility and what it really means to be compatible, and I'll get to that in just a bit. The second key pillar that we like to talk about is serverless. And with serverless, you actually get true scale to 0. And I call that out because we hear from customers again and again and again around what does serverless really mean, right? So I'm going to take a second and share what we as Keyspaces think about serverless. With serverless, there's obviously no instances. You're not going to the console and choosing R5 or C5 or any of that. But in addition to that, you don't even have to worry about capacity. You just create a table, you put reads and writes on that table, we figure out all the underlying compute, infrastructure, storage, etc. for you. Let's say you're not putting any reads or writes on the system. You don't pay for that. So you actually pay for what you use. If you have 0 reads and 0 writes, you pay $0 on Keyspaces, giving you the true serverless promise of scale to 0. Now, you might be wondering, OK, what about performance, right? Cassandra is really good at performance. What about Keyspaces? Well, we give you the same single-digit millisecond performance latency on pretty much most of your queries at any scale. So let's say you're going from gigabytes to terabytes to petabytes. Your database is not slowing down. Keyspaces is still horizontally distributed like Cassandra, and you keep getting that single-digit millisecond at scale as your workload grows on Amazon Keyspaces. Last but not the least, availability and security. This is job 0 for us at AWS. We provide 4 nines of SLA. What this really means is, if you have an availability requirement for any tier 0 apps, that's kind of a checkbox. We provide that. You get 4 nines of SLA within a single region. We keep 3 copies of your data across 3 availability zones. You only pay for 1, but we make 3 copies for durability. And we offer features such as encryption at rest and encryption at transit by default. So you don't have to go and set any of that up. You just create your first table, and you get encryption at rest and encryption in transit right out of the box. Now, your next question might be, who is using Keyspaces, right? And what are the use cases? We'll start with Amazon. We use Keyspaces for internal workloads for a variety of use cases. Externally, you're going to hear from Intuit very shortly why they use Keyspaces. We also have customers such as Experian and PwC who use it for financial tech applications. We are starting to see additional workloads in different verticals, such as time series and graph, which is definitely newer for us as Keyspaces, being in the market for about 3 years now. So the point I'm trying to make here, that it's general purpose. We've seen customers across verticals and segments adopt Keyspaces. I've shown some logos here, but that's not the entire list. You can click on that link below. You can see some more examples. We also have some customers that publicly aren't referenced yet, but soon will be added over the next few months. So keep an eye on that page that I've linked below. Now, let's talk about a very popular and a favorite topic from a lot of our customers around Cassandra compatibility. So what do we mean by Cassandra compatible? And I'm going to raise my hand and say up front, we're not 100% Cassandra compatible. There are some features that we don't support that Cassandra supports. But our goal is to be 100% compatible with what our customers are using. What that really means is we work backwards from your requirements. Some examples of features that we've added in the last year include the Spark connector support, TTL support. Those were some feature asks from customers who use Cassandra heavily, wanted to use Keyspaces, but couldn't due to these missing gaps. So we're always working backwards from those customers. We have an action-packed roadmap for the rest of Q4 in December and Q1 and Q2, where we're going to launch additional compatibility, especially if you're using query APIs that we don't support today. We've also built a tool that you can run against your source Cassandra cluster, and it'll spit out what features that you're using today that may not be compatible with Keyspaces. So you don't actually have to go and try a POC, spend a lot of time, find a surprise. We tell you this up front. If you're interested in using this tool, come talk to us after, and I'll be happy to connect you with the right folks. Versions. So we are compatible with version 3.11.2, backward compatible up to that version. I know there have been additional versions out there in Cassandra. 4.0 is available. 4.1 is in preview/release candidate. So we're committed to supporting additional versions. Where we see critical mass today is up to that 3.11 kind of version range. So we're compatible up to that version. All existing tools and drivers, pick your favorite language. Python, Node.js, Java, Perl, Ruby. Existing Cassandra drivers for these languages or DataStax drivers continue to work with Keyspaces with little to no change. Another very popular question we get is, what about tombstones? What about repair? How does garbage collection work? Or how does compaction work? So the good news is, as a developer, you actually don't have to worry about this on Keyspaces. What I was talking about earlier on the architecture side, and I'll cover that just in a bit, We don't completely use Apache Cassandra under the hood. We use parts of it, but we've also built our differentiated storage architecture that makes some of these concepts redundant or not applicable. And if they do apply, for instance, garbage collection, obviously there's some version of it that we also applies to Keyspaces, something you don't have to worry about. We take care of it for you completely without any application impact or a setting that you need to tune, adjust, or deal with. So next time a developer at your company asks you, hey, tombstones, how do I deal with it? And if you're using Keyspaces, the answer is, hey, you don't have to deal with it. It's done for you. You keep driving traffic, terabytes, petabytes, millions of reads, millions of writes. It's just taken care of right off the bat. And now, let's talk about the architecture. How does this really work? How have we gotten rid of tombstones? How can we get serverless? How do we get petabyte scale? The key point to talk about here is that compute and storage and Keyspaces are completely decoupled. So your nodes on Cassandra may be data-bearing. They're heavy, they're data-heavy. On Keyspaces, that's not the case. On Keyspaces, your storage partitions continue to grow in 10 gig increments. So let's say you have 10 gigabytes of data today. Your workload grows to 20, 30, 40. Your company is wildly successful. You're getting into terabytes, hundreds of terabytes, into petabytes. On your partition key, we use sharding under the hood. We keep scaling your storage partitions as your data size grows. This is automatic. You don't have to go to the console, click a button, or take any application downtime. Now let's talk about the query processing layer. That's the compute layer, or what we like to call the compute layer. This is where your reads and writes go. This layer also scales independently of storage. So let's say you have very thin storage. Maybe you have just a couple of gigs of data, but you have thousands of reads and writes per second or millions of reads and writes per second. You're able to achieve that with our separation. Your compute layer also scales automatically on your partition key, and you don't have to worry about scaling your reads or writes either. You can let Keyspaces take care of that for you without any application impact. So that's our architecture in a nutshell, and if you want to go deeper, we'll be happy to, like I said, stick around or take Q&A towards the end of the session. Now let's talk about serverless. The key point I want to call out here on serverless is what it really means. And we talked about scale to zero, but how do you achieve that? So in Keyspaces, there are two pricing modes, and this often trips up a lot of customers because if you're coming from a Cassandra world, you're so used to vCPUs and memory that it's a little bit different on Keyspaces. So in Keyspaces, by default, you get started on on-demand capacity. What this means is that you actually don't provision any amount of compute. You just go create a table, you put workload on your table, and over time, Keyspaces learns how much capacity you need. And it's not magic. We learn about your workload, we see your average reads and write, peak reads and write, and we provision the underlying infrastructure for you as your workload grows. Now, you may be a customer who may want some more predictability. We also give you an option to provision a certain amount of throughput, and this is not instances. You're provisioning a certain number of reads and a certain number of writes. That's a second pricing mode, and that's what we call provision capacity. The good news with provision capacity is that you can still use auto-scaling. So you can set up a minimum bound and a maximum bound, and we will scale within those bounds of reads and writes. Everything you're doing on Keyspaces is in terms of reads and writes. There are no instances, there's no RAM, there's no CPU. You directly get billed for your database operations in reads and writes. That's enough about Keyspaces and enough from AWS. I'd like to now bring on Manoj and Jason, and they'll kind of talk to you guys about how Intuit migrated from Apache Cassandra to Keyspaces. Pass it on to you, Manoj.
Hello. Thanks, Meet. Hello, everyone. I'm Manoj. I lead a platform engineering team at Intuit. So myself and Jason, we are excited to share our Keyspaces journey with all of you. So this is a code we had published earlier in an AWS case study. Our prior state used to be a custom Cassandra cluster running on AWS. In this prior state, we would need to do extensive planning every time we have to add additional capacity for organic growth in our cluster. And this extensive planning would translate to at least a few weeks of lead time. Now, with Keyspaces as a managed service, we are able to accomplish all of this in a single day and save on all of this energy and bandwidth and repurpose that towards building business capabilities in our platform for our stakeholders. Quick introduction about Intuit for folks who don't know. Intuit is a global fintech company, and our mission is to drive financial prosperity around the world. We do this by building AI-driven expert platforms that enable our customers to better manage their finances, be it tax solutions using TurboTax, or be it personal finance solutions using Credit Karma or Mint, or accounting automation for small businesses using QuickBooks, or even marketing automation leveraging MailChimp. We continue to innovate, building best-of-breed financial solutions, and are currently serving over 100 million cumulative install base of customers globally. Quick introduction of our team. Our team is known as the Intuit Data Exchange Platform team. Our charter is to acquire information working with several different financial institutions and data providers globally as a one-stop shop for all of Intuit. So we go ahead and build data agents that acquire this information on a continuous basis, and then we pass it through several different cleansing routines, and then make this information readily available in the form of services for all of the Intuit products in the specific use cases of those products for our customers. Now, this is a very high-level overview of the landscape of our platform. Now, as I mentioned, what you see on the right side of the diagram are all of the different integrations and capabilities that we have built in the form of custom agents to extract this information. Once we extract this information, this passes through several different routines, like cleansing routines, curation routines, enrichment routines with ML, and so on. And finally, all of that data gets persisted in what used to be our Cassandra cluster. To the left side of the diagram are all of the Intuit products that is requesting for specific information in specific use cases in the form of several different APIs and services from our one-stop platform across the board. Now, all of the different logical application components are containerized and deployed on Kubernetes pods for seamless scalability. Please note that this is just a very high-level forest view of our landscape of our platform without delving into the finer details in the interest of time. Let me pass it on to Jason to walk through the next few slides.
Thanks, Manoj. So our group has been running a Cassandra cluster now for going on 8 years. Our use cases primarily involve storing and retrieving large volumes of financial data. And since we don't require complex queries or table joins, we chose Cassandra primarily for its horizontal scalability and its performance. And I think that for the most part, Cassandra has delivered on these aspects, but it's certainly not without its downsides. Operationally, it requires some significant effort. There are administrative and monitoring tools to install and maintain, a backup strategy needs to be put in place, and things like version upgrades, scaling out the cluster. These all need significant planning and execution, ideally by someone with that specialized skill set. In our group in particular, we had the rather unfortunate situation of having multiple periods of time where we didn't have a DBA assigned to these tasks. We ended up going so long without running some of the important maintenance jobs like repair that we were actually told by DataStax that starting them up again could impact the entire cluster. So towards the middle of 2019, one of our team members was starting to look into DynamoDB as a possible fit for our use cases. And while it looked promising, it would have taken some significant application level changes on our side to really integrate with it and test it out. So later that year, when Keyspaces was announced as more of a drop-in replacement for Cassandra, we were very eager to try that out. We ended up taking one of our services in particular, called Financial Transaction, which had by far our largest volume of data and highest processing requirements. Around that time, I think it had around 60 billion rows in the database and was serving anywhere from 2,000 to 8,000 API calls a second. So we chose this service to do a proof of concept with the idea that if Keyspaces performed well with its volume, then it would also be suitable for any of our other services.
So in summary, our platform, specifically our persistence layer, was doing all of the essential things expected with some additional maintenance overheads. We were able to take all of our existing workloads up until that point in time. However, the Intuit product landscape was changing with newer acquisitions like Credit Karma and MailChimp. And this meant our own platform needs continued to grow. Our workloads were quadrupling over time, and there was a significant increase in the variance of traffic that we were seeing on our platform. And all of this, we had our database being the single biggest choking point in the platform ecosystem. So all of our existing workloads were more along the lines of the small aeroplane that's depicted out here, but we were now looking to upgrade our persistence layer from being this small aeroplane that could take only that minuscule amount of traffic to being more like a Boeing 777 that could really push the boundaries of scale. So now that we have the problem statement defined and called out clearly, we wanted to strategize on how we roadmap towards a solution. In order to do that, we prioritized 4 key aspects as we were working through this. 1, we wanted to leverage persistence as a managed service. This way, we could put away with respect to all the operational and administrative overheads. 2, we wanted to stay focused on delivering business agility for our customers. We did not want our database layer to be the slowest moving block in our platform ecosystem. 3, we wanted to dynamically scale up or scale down all of the capacity so that we could keep our AWS costs optimal in the longer term. And 4, we were also keen not to overhaul any of our application or data service contracts, because this way we could focus on this being a seamless upgrade without having any sort of adverse impact for our stakeholders of the platform. So for all of you who are thinking, did this team really evaluate DynamoDB as a potential option? There lies the answer, right? This was the reason why we were inclined to move ahead with Keyspaces as our first priority. Looking back through our journey, there were 3 key decisions that enabled us to get to be in this successful state of launching Keyspaces. What do I mean? Let me talk through. 1, beginning all the way from the beginning, working with AWS, we knew that Keyspaces was not Apache Cassandra under the hood. What this also meant is we had to ensure that there was a high level of parity functionally as well as non-functionally to ensure that there is zero to minimal adverse impact on our application layer. 2, we wanted to simulate this entire setup in production in an iterative way. Our platform is extremely mission critical to all of Intuit, and we did not want to sign up for a higher risk quotient given the critical role we play in the Intuit ecosystem. So in terms of a risk mitigation strategy, we wanted to continuously iterate and figure out and get to our final state without it being a 0 to 1 transition. The third one, we wanted to build out a strong partnership with AWS engineering and all our cross-functional teams. Now, in my opinion, this was probably one of the most important investments we made as we embarked on this journey. This helped us set the right expectations all the way from the beginning, enabled us to lean in on AWS as we ran into different sets of roadblocks and get help right away. It seemed as if both our teams were connected at the hip all the way from the beginning till the end. Okay, now that we have the problem statement followed by the strategy and priority around what we are solving for, we wanted to now make sure that we break down the entire goal into a sequential, logical set of milestones or phases so that we are dividing and conquering it appropriately. So we came up with 4 different phases in terms of getting to our end state. Phase 1 is all about dual writes. What do I mean by dual writes? We wanted to simulate all of our write traffic, the actual production write traffic onto Keyspaces in a simulated manner, actually running in production. This enabled us to stay focused on solving for all of the write-related challenges, be it write throughput, write performance, optimizations, etc. Right? So that was our focus of phase 1. Phase 2, we did the exact same thing with reads. We wanted to make sure that we are simulating reads from Keyspaces while our production is still the Cassandra cluster, and ensure that we are comparing apples to apples between our current state of production and the new simulated reads from Keyspaces. Phase 3 was focused on data migration. So data migration was about the one-time historical data backfill from the Cassandra to Keyspaces. Dual writes was for all of the ongoing writes that's happening, and the data migration was only the one-time migration. Now, given that we were one of the early adopters of Keyspaces, there was no data migration utility. So working with AWS, we choose to build out a custom migration utility. And phase 4 was all about data parity and then cutover of traffic. After phase 1, 2, and 3, we had all of the writes, we had all of the reads, and now it was time for us to ensure there was 100% data parity at a row level, at a column level, between the old system and the new system. And then once we had guarantees on that data parity, we slowly, gradually moved our users in batches from the old system to the new system. So these were how we took as the approach. Now to deep dive into each of these phases and explain all of the challenges, let me pass it on to Jason.
The Cassandra. Keeping with the principle of zero customer impact during this evaluation, we made the writes to Keyspaces fully asynchronous and added the appropriate safeguards so that any issues with that write path would not affect any of our user requests. When we first rolled this out, we actually saw a very high error rate. Around 40% of our writes were failing. And even after implementing some of the recommended best practices, like retries with exponential backoff, we still had a significant error rate, as well as some high latency now because of those retries. At this time, we were meeting regularly with the Keyspaces team, and we worked with them closely to dig into the issue. What we found was that we were hitting a rate limit. So Keyspaces has a few different levels of rate limiting. There's an overall limit for the AWS account. There is a limit per table. And we were aware of these, and our monitoring showed that we weren't anywhere near hitting those limits. But there is another limit when reading and writing to an individual partition within a Keyspaces table. You can see above, our most heavily used table was storing all financial transactions for a given user and account inside a single partition. This meant that if we had a user with a particularly active account, we could easily get into situations where a single request coming into our service would result in thousands of rows being inserted into this single partition in Keyspaces. And when we do this, we do make multiple parallel requests to Keyspaces to try and do this as quickly as possible. And while doing so, we were just repeatedly hitting this rate limit. So working with one of the solutions architects, we did some ballpark math around how long it would take to insert different amounts of data given this limit, and quickly came to the realization that given the way that our data was partitioned, we just weren't going to be able to meet our latency objectives. Again, the core issue was that we were trying to insert too much data too quickly into a single partition. So the recommended solution was fairly straightforward. We added another column to our partition key, which essentially spread the transactions for a given account over multiple partitions. Based on our volume, we found that using 10 partitions should give us throughput comparable to what we had in Cassandra. And when we implemented and rolled this out, we saw very good results. The latency was now within a few percent of Cassandra in all the percentiles that we were measuring, and the error rate had dropped to almost 0. I say almost 0 because even after making this change, there were a small number of updates that were still continuously failing. When we looked at the error messages, it looked like they were all the same message, which was we were exceeding the maximum row size of 1 megabyte. When we dug into why this was happening, we found it was all due to one particular use case that we have around pending transactions. Because of the way that these are processed in our system, we store pending transactions differently than we do our regular posted transactions. Rather than putting each one in its own database row, we take the whole list of pending transactions for a given account, serialize it to a JSON string, and stick that into a text field inside one row. Normally, this list is very small, but for a few of our larger customers, there were several hundred of these. And in this case, the resulting JSON string exceeded the 1 megabyte. So we did check at this time with the Keyspaces team to see if we could just increase this limit, because some of these things are adjustable, but this is a hard limit. So definitely something that needs to be kept in mind when designing your database schema. After discussing a few potential options, we ended up implementing client-side compression. So compressing the data right before inserting it into Keyspaces, and then decompressing it again when it's read back out. After implementing that change, the write errors dropped to 0. So now that we had confidence in the write path, the next phase was essentially doing the same thing for reads. Here we modified the read path such that every time we performed a read in Cassandra, we would perform the same read in Keyspaces and compare the data. The data comparison was especially important here because even though we had confidence in the write path, we still didn't know for sure if this dual write strategy would really be good enough to keep the databases in sync. One challenge with the approach is that the writes between databases are not an atomic operation. So the way we were handling this was we would write to Cassandra first, and if that succeeded, we were relying on our retries to make sure the data was also written to Keyspaces. From our monitoring in the first phase, it looked like this was working, but we needed to validate the data to be sure. So when we got the initial results of this phase, things looked really good actually right off the bat. The error rate was very low and similar to what we had in Cassandra. And the latency across the 90th and 99th percentiles was also very similar. When we started looking at the higher end latencies, however, the performance started to diverge with some very high latency requests in Keyspaces. Looking at the max, you can see that Cassandra was about at 2.5 minutes, whereas Keyspaces was almost at 2 hours. Now, to be clear what we were measuring here, this wasn't a single request in response to Keyspaces. Rather, it was a series of requests iterating through all of the different pages of a select query. We were monitoring it at this level because due to the schema change that we made in the first phase, the select queries between databases were now different. So in order to get an apples-to-apples comparison on the latency, we had to measure it at this level. Here's a quick example of how the query changed. In Cassandra, we were asking for all transactions for a list of accounts. And now in Keyspaces, we were doing the same thing, but with the added list of partition IDs. When we looked at the specific cases where this query was taking a long time to run, we were actually very surprised to find that in certain cases, we were asking for all transactions for up to 20,000 accounts at one time. What this meant was for the Cassandra query, it would have to scan through 20,000 partitions on the back end, whereas Keyspaces with the additional list of partition IDs would have to scan through 200,000. To make matters worse, we found that at the time, the back-end processing on Keyspaces was doing all of this work sequentially. So from this point, the Keyspaces team started working on an enhancement to do some of that back-end processing in parallel, while we continued investigation on our side. One strange thing that we had noticed was that although we were asking for transactions for so many different accounts at once, the actual number returned was only a few hundred, meaning that most of the accounts had no data at all. When we dug a bit further, we confirmed that this was actually the case. One of our other services, called Financial Account, had a defect that was sometimes inserting duplicate rows into its database. Because of the application logic in that service, these extra rows were never getting returned to our customers, but when they were used to generate this transactions query, they weren't getting filtered out. So the end result of this was that both Keyspaces and Cassandra essentially were spinning their wheels on the back end, looking through thousands of partitions that would never actually contain any data. And this is what was causing the high latency. After the Keyspaces team rolled out the enhancement on their end, and after we fixed the defect on ours, that original 2-hour query dropped to about 30 seconds, putting it almost exactly on par with Cassandra. So now that we had verified the latency and the error rate of the reads, the other important part of this phase was the data validation. The way that we implemented this was that every read that we did in Cassandra, we would perform the same read in Keyspaces and compare the data. The results of that were logged, fed into a dashboard, and we reviewed that daily to make sure that the data was being kept in sync. When we first rolled this to production, the report showed that we had data mismatches in about 1% of the transactions. However, when we spot checked a few of these looking directly at the database data, we didn't see any mismatches there. What was happening was, because we were leveraging reads that were happening within the application, the chances were fairly high that that same data was being updated around the same time. And because we were doing asynchronous writes over to Keyspaces, sometimes the comparison was happening before Keyspaces was actually updated. So this was fairly easy to work around. We, instead of leveraging the reads that were happening organically in the application, we just set up a process that ran off to the side that compared the data in the background. After making that change, the original 1% of mismatches dropped to 0.01%. Looking at the remaining discrepancies, we found that those were actually due to data inconsistencies in our Cassandra cluster itself. Cassandra's model of eventual consistency does allow data to remain inconsistent between replicas for some time. And in our case, this was exacerbated by the fact that we couldn't run repair. And because we were using local quorum consistency when selecting the data out of Cassandra for comparison, it was possible that these inconsistencies would show up on our mismatch report. The fix here was to use consistency level all when selecting the data out of Cassandra, which guaranteed that all 3 replicas would always be consulted, leading to consistent and up-to-date results. After making that change, the reported mismatches dropped to 0. So at this point, we had validated both the read and the write paths, and additionally, we had created a point in time when we turned on the dual writes, such that after that point in time, the databases were in sync. So the next phase was backfilling all of the historical data that still resided only in Cassandra. And now I'll turn it back to Manoj to talk through some of the details of that phase.
Okay. Thank you, Jason. So now that we have all of the dual writes and reads working in our production setup, it was time to focus on data migration. Now, for all the Cassandra experts out here, the immediate question that comes to your mind is, why do we need a data migration utility? Why not just stream the data via replication from the current Cassandra cluster to the Keyspaces instance? Well, there are a couple of different reasons why we could not pursue that route. One, as we mentioned before, AWS Keyspaces is not Apache Cassandra under the hood, so that was not a viable route. Two, our own production cluster, Cassandra cluster, was maxed out on I/O operations bandwidth. So we were less than keen to let replication run on our production cluster that could, that is a heavy I/O operation and hog all of our production bandwidth, potentially disrupting work for our customers. We would never let that happen. So with these reasons and with these constraints, we choose to build out a custom migration utility. And we use this utility one time to historically backfill all the information. Now, even with that utility, we built in the right level of throttles such that we would maximize the migration workloads only when our production workload or production traffic is less. So this way, and the vice versa too, right? And this way, we were able to leverage the max capacity based on our production Cassandra cluster without creating any problems for our customers. So this is a quick glimpse of how auto-scaling works in Keyspaces. The blue line indicates the provision capacity, and the green line shows the consumed capacity. Around 3:28 p.m., in this particular instance, the total write consumption starts to peak, and the provision capacity automatically scales up with just few minutes of delay. So what this ensures is, if you have your auto-scaling configuration set right, your system can seamlessly scale without creating any kind of adverse impact for your customers or production workloads. So up until this point in time, our Cassandra cluster is primary, and everything that we are doing on Keyspaces, be it reads, be it writes, was all in a simulated manner in an asynchronous fashion. And the asynchronous fashion ensured that if there were any glitches on Keyspaces, that would not result in any kind of production impact for our actual production system. We continued to do this. We continued to monitor our system in this setup for an extended few sprints until we ensured there was 100% data parity between both the systems, and two, that we were able to build a high confidence that the new system is up and running and in a steady, stable, mature state. And once we got to that high confidence phase, then we started switching over the reads and writes to be primary and synchronous on Keyspaces, and then gradually we started terminating or tapering off all of the reads and writes to Cassandra. So this is how we made the switch over an extended period of time, iteratively working through all these phases. To give you a glimpse of the high-level stats with respect to our Keyspaces implementation, our peak time writes is about 15,000 WCUs. Let me take a moment to explain what WCU is. It's write capacity unit in Keyspaces. One WCU represents one write per second for a row of up to 1 kilobyte in size using local quorum consistency. So if your average payload size is 3 kilobytes, then each of those payload requests would translate to 3 WCUs in Keyspaces. Peak reads was 140,000 RCU. Similar to WCU, read capacity unit represents one local quorum read per second or 2 local 1 reads per second for a row of up to 4 kilobytes. Our total data footprint was about 150 terabytes, which comprised of more than 100 billion records. Okay, where we are today. We have been fully live on Keyspaces implementation for the last 1 year. We have had 0 production incidents post-migration to Keyspaces, specifically around our persistence layer. Now, this was a huge feather in the cap for our team, primarily because database layer used to be our single biggest contributor towards all of our production incidents. We have also significantly improved on our operational metrics, like reliability and availability of our application. We've been able to avoid sporadic read timeouts that we used to see on Cassandra and so on. And we were also able to deliver on all of our agility goals to enable better business capabilities, leveraging our platform for our stakeholders. So this is all the content that we wanted to share from Intuit. So let me invite Meet and Jason back on stage to wrap this session up.
All right. Thank you, Manoj. Thank you, Jason. I think that wraps up what we have for you all today. Again, appreciate you spending time and sticking around later in the evening. You see a link to the survey on your app. You came to the session, you registered for the session. We really encourage you to take the survey. That's how we learn. That's how we know what to do better next year. So please take the survey. Let us know what you thought so we could keep making